Any more question about the thing? Okay.
So could you please repeat what's the difference between semi-supervised and unsupervised in a nutshell? In few words.
As I said, semi-supervised is when your data is actually clean. It's like you're sure that whatever you have has nothing to, like there is no outlier in it. So you can. So the difference is like that. It's like for k-means or all those models. The thing is, you're saying for KNN, you're saying that if the distance of one of the sample is too much from the rest, maybe that's anomaly, because your assumption is outlier is already in your data, and based on some distance, you want to learn it. But if you know whatever you have is normal, then you don't want to learn some outlier from it. You want to just learn the distribution. Maybe you want to learn whatever inside, and then from that moment, you want to say whatever is not similar to the thing that I've seen before is outlier. So you can have different technique for it. Like for, I don't know, for GMM is basically when you kind of have semi-supervised one because you want to fit some distribution. If you have a bunch of noise in your data, you will learn those data as well. So you better have a clean data before GMM, or you better have super sparse of them, and then that's why you have to have a threshold. So it means if you are confident that the data is clean, then maybe you can do different things. Like next week we'll see. Next week we'll try a bit of. We'll start doing deep learning model as well, which will be like a deep generative model. Like simplest one will be autoencoder. And for autoencoder, the thing you are trying to do is you're saying that whatever I have is normal. That's why I want to learn a model that can reconstruct it again. So so it means your assumption is the data is clean. And if you know that you have lots of noise in it, then maybe you have to use different approach.
So that's why for semi-supervised, you will only use it if you know that your minority class is very, very few.
Yes, kind of, yes. I mean, that's a kind of definition of outlier in your data set. But the only thing is in supervised, you know whatever you have is actually clean. In unsupervised, you know you have them as well. So that's just a two different category. Okay, I have defined some function that you will use it during this session. One of them is finding the best threshold. The other one is evaluation. For the evaluation one, here I'm just saying that if you have any, if you have for the test for the testing of this hypothesis, I'm just saying that if you have the label, and if you have kind of like a prediction, which basically say if you're using any kind of model for finding any kind of outlier, it can be based on KNN, can be based on clustering, 1STM or anything. Then here I'm trying to compute some score. It can be precision, recall, F1 score, ROC, and then we will see confusion matrix as well. And based off this metric, we should be able to compare these techniques together. It's like the only way that you can say if, okay, so it means the thing that my assumption here is like you have at least some small label data that you can use to compare this technique. And maybe that would be kind of like a essential if you want to actually compare any kind of model. So it means usually you won't have access to any kind of outlier or anomaly or any rare event or anything like that in your data. But it's always helpful to at least have access to at least super small portion of it. Maybe you can ask some person to find some outlier in your data. If it's a credit card, maybe you will have access to some small fraud that someone will tag it for you. And then it's not enough for your training, but you can use it as a test. And that's maybe the whole idea here. It means you have label data, but it's super small that you can use it for training, but you can use it for the test. And if you have that data set, then you should be able to train multiple models on your training data, and then based on those small amount of label data, you should be able to compare them and see which one is the best one. And to be able to do that, we better use like some metric like precision or recall, which the only thing that they care about is like if you have, let's say 100 let's say fraud in your data, how much percentage of them has your model covered. So that's recall. So you're saying that if you want to actually define all the fraud in your data set, you have to just look at the recall, not accuracy, not maybe even precision. It should be recall. But if you look at if I don't know, someone asking that whatever you are saying is fraud, it should be fraud, because I don't want to go and talk to person and say, you want to say they want you to be confident about your data. So then you're saying that the percentage of the thing that you're saying is positive should be positive. What's the percentage of it is actually positive? Then is precision. So that's why, based on your application and the thing that you're asking for, you can look at the precision or recall. So that's why I'm trying to kind of show you the result as well based on precision and recall. And F1 score is a kind of like a combination of these two together. The other thing is the visualization that you will use for this session. So far everything was about the data, the loading, and some of the function and evaluation function that we will use during this workshop. So isolation forest is one of the first technique that you want to see how it will perform. Just as a reminder, as you might remember from the video, isolation forest is a technique similar to random forest, which we have maybe heard of, which basically is an ensemble technique. It means instead of making one model, the idea is you can have lots of models, and each of them will perform maybe poorly, but if you have enough of them, combination of them will work a lot better. So that's the whole idea. Is like you can have lots of kind of weak model. In total, it's like a voting system. In total, you will have a good score. And here, isolation forest will try to make lots of isolation tree, which will basically sample the data, randomly pick a feature from it, and randomly will cut it. That's why isolation forest is one of the fastest kind of technique here, because it's not computing any distance, it's not computing that much, like it won't be like a one stream that will try to find a boundary. The only thing that it's doing is randomly picking some samples, randomly picking features, and randomly cutting it. Everything is kind of like a random. But the idea is if you have enough of those random, then you should be able to get good number. Is it clear to everyone? Nook.
So here, it really is random, right? There's nothing to guide it towards making better cuts.
No.
Okay. So is there like something like an XG boost, but like for this? Because then you could kind of guide it.
Like for XG boost, the thing is like that. You have label. So XG boost is you won't be able to do something like XG boost here, because XG boost like that is XG boost. The difference between random forest and XG boost is XGBoost is sequential. It means in XGBoost you are training one tree. Based on the result of that tree, you are training the second one. And then you're based on the result, is like sequential. You can't train them in parallel. But here you can train them in parallel. It's like a random forest. Because random forest, each tree doesn't care what was the result from the other tree. It's just trying to get a good number here. And the other thing is, then you have the label. So you can say what was the accuracy of the model. But here you don't have access to any kind of label, so you have no idea how good is the model. So then that's why you can say, so in XGBoost it's kind of like once you say that, oh, I mislabeled that sample, I should increase the weight of it for the second tree. But here you can't do that because you don't have any label. That's why you have no idea what you're doing. That's why here you're just saying that, so maybe the whole idea behind it was, if you randomly cut in different dimension, if a sample is kind of a bit far from other node, if you have enough tree, you should be able to isolate it a lot easier than if you have lots of nodes super close to each other, because then it will be super hard. Even if you do it in any random way, because they're packed together, it will be super hard to do that.
Do you cycle through dimensions, or do you use each dimension on the once?
It's like, okay, it's like a tree. So per node, you're randomly picking one feature,
Yeah.
and then you're doing a cut. For the
With
second one,
replacements.
with replacement. For
So-
the second one,
So there is a chance that for the second I pick the same
yes,
feature.
because
Got
you
it.
have to kind of, because it's like a regressive, it's like a recursive model. Because as you might remember,
So yeah, I remember the picture.
so
and
here
in
you
the
just,
picture it was
yes.
like that.
So if you have two feature, if it was just once, it means you can just do one line. But here you can have multiple lines. So it means yes, you can select the feature again to be able to do another cut. But the thing is, even another thing that actually you can do, and isolation forest is like, instead of just picking randomly, you can have a subset. Each time you can have a subset of those features and then pick randomly. So you will, even you can, as an exercise, you can try that one as well. But the whole thing is, each node is kind of independent from the other one. So it's like a sub-spacing problem. One node will divide or split the space in two, and from that moment, you will have two nodes, right? Then each of these nodes will treat the data completely differently, because one of them just looking at maybe the right side of the data, the other one just looking at the left side of the data, and then each of them try to do some cuts to be able to isolate node. So, and then they will pick a feature, do the cut, pick the feature, do the cut.
How is the random value selected?
Is then between minimum and maximum, it will pick something randomly.
Okay.
That's what I'm saying. It's
Just
like a pure random. It's like, as I said,
uniformly random.
yes. So as I said here, random subsampling of the data. So even to make, you're not looking at the whole data. You're kind of making a new training, or new data set for yourself by sub-sampling from the data. Maybe you're just looking at, let's say, 10% of the data, and then randomly selecting a dimension or feature, random cut to a subspace. Again, for the next node, you're doing that again and again and again to isolate a node.
Why do we subsample just to?
Because the idea here is like, if you, let's say for one of those, let's say for credit card fraud, we have almost like 300,000 nodes, or for image it can be, the number of samples you have might be 1 million. And if you have 1 million, no matter what you do, isolating a node would be super hard, and the tree would be like super large that you won't be able to handle it.
Right.
So that's why you're saying that even if I subsample, if an area in the space is dense, by uniform randomly selecting node, still I will have more samples from that area than a place that which is like a super sparse. So that's why. And then if I average all these models again, because at the very end you're averaging them, kind of, you're saying that what's the distance from each node to the root. If you average them, then you will have a good number. So that's the whole idea of isolation forest. So it's not like a super crazy magic. The whole idea is, if someone randomly do some cut, and if lots of people do that, if something is rare, and so it means it will be further from the rest, it will get cut, and the score for that will be higher.
So how does it deal with correlated features? Because like every single time you just do one.
Yes,
one
per feature, exactly. So that's the thing. For there are some technique that they are dealing with that, but the pure isolation forest, as you said, each cut is kind of in parallel with one of the axes of your data. So it means it would be per feature you're just doing one cut. The cut won't be kind of like it won't have any it won't be like a complex cut or any sophisticated one. It will be just a random cut per feature. So
per features.
Why is this an issue?
Why is it an issue?
Because sometimes if you look at the data, you will say, oh, if you maybe do the cut in that way, you should be able to easily isolate one node instead of doing that multiple times. But exactly because the whole idea here is you know nothing about the data. Then why should you care, because you don't know that? That's why instead of trying to deal with that, you are just doing that per dimension, and you're hoping that if you have enough of them, you will be cool. That's why here I'm going to show you that it's actually working or not. So see here I have this number here, and you can see for sure this node is anomaly, right? So each sample has 2 features. And then here I'm just saying that number of estimator equal to 2, so it means just 2, 3, and do lots of cut and fit. And then I'm just adding more 3 to that one, and then I'm doing that again. So if you look at it, even both of them saying that these 2 numbers are different. They can easily isolate them. But if you look at the score, you can say the score for this one, the distance from this, the score for that one is a lot higher than even the last one. But they're saying that both of them are different from the rest. See, these are either 0 or negative. This one is completely positive. This one is again negative and positive in 2 different dimensions, but the value is super high. So see, they can kind of find these things just based on cutting randomly in each feature. And I'm just trying here to show you that it's possible. But the thing is, if I do that maybe multiple times, the value will get changed. But I'm just trying to see here, this time, the one which has just 2, 3 said that even the third one is anomaly. But when I had 23, it didn't happen. So it's always the last 2 which is anomaly. So it means if you have enough 3, even if you do the cutting multiple times, the result won't change because you have enough of those 3. So on average, the result will be like that.
What's the second number?
That's the kind of like let's say the average. You can call it like a probability, but it's a distinct function. It's like, because each of these numbers actually the average of the, let's say, distance from a node to the root. So if you're doing multiple cut,
why is negative though?
So that's that's how isolation forest trying to divide it by scaling. So then it make the 0 to be kind of like the
average.
Yeah, the one that the threshold for you that you're saying that if anything is negative or positive, is anomaly or not. But if you want to implement it yourself, then yes, it shouldn't be negative, because that would be just one, would be just a distance, and then the thing would be like what should be the threshold based on distance. You can decide. So as you can see, I was just trying to show you that it's actually working even if you have a small amount of data.